So hi guys. Last time we discussed some performance tips and more advanced configuration scenarios. So today let's continue where we left off on Wednesday, and later we'll also look at some debugging possibilities of Visual Studio to help us debug current applications. One thing I mentioned last time is that RabbitMQ library creators use thread pool QE work item in some pieces of code in order to optimize it further, not to create new tasks. Well, they're not just using QE work item. They're also using a state pattern, which I'll just show you right now. So as you can see, QE work item, it accepts a delegate, wait callback. And this wait callback is a delegate that accepts some state object and returns void. So in the past, when we looked at this example, we just used a delegate here that just did something inside, and it did not use that state object. However, let's imagine that we need to do something like this here. Where name variable declared outside of the scope of this delegate. In this case, this would introduce, we need to pass state object into the delegate in order for it to work, which we do not use here. In this case, this was introduce a closure. So in order for this delegate to access this variable name, a new type of object needs to be created, which will be a closure that will contain this variable and this delegate. And this delegate will be able to read this variable value. This allocation of separate closure is also takes some time from CPU and some resources. So in order to avoid that allocation, you can always instead of capturing some variables in this way, you can pass all the variables that you need inside that delegate in a state object. For example, here we need just name, so we can pass that name as a state. How we can do that? We can pass here a second parameter into this method, which called state. And as state, we can, for example, pass name. And here inside, instead of using that variable that we are capturing, we'll just use the state variable that is coming here to us into our delegate. Which will reduce allocations because now we are not capturing any variables. When we are creating tasks, we can also use state pattern. So this pattern is it can be used in many places when you really need to tweak that performance a notch. Let me just show you an example what exactly is a closure, just so we all understand. So here, for example, this delegate, it needs the variable year. Let's, for the sake of simplicity, just comment this out and write here I. This delegate needs a variable I, so it captures it. It captures this variable from this loop for. And from I 0 to 100, we are running the delegate that will print into the console the value of I. But if you run this example, you can see that, let me just remove the breakpoint as well. You can see that all the values that were printed is actually 100. Well, not all of them, but some of them were 99, 84, but the earliest value that we have is 80. 40, 42. Why is that? Because we have a for loop, and what does for loop do? It takes this variable and it increments it one by one. And here, when the capturing of this variable happens, so that this delegate can use this variable, .NET creates for us that closure with this variable, and it passes this variable by reference. So now every task run operation creates a new operation to be run on background thread, and this operation, it has a reference to this variable that is actually being incremented right now for by a for loop. So by the time all of them are executed, most of them are executed, I is already incremented into 100. So in order to fix that, we can do this, for example. We can create a new variable and assign it to I. And whenever we create a new delegate now that will run in task run, it will capture this variable. So for every iteration, this variable will have its specific value for that iteration. This is what Clojure does, and it incurs additional performance issues. I mean, they are very, very small, almost negligible, but in a library like RabbitMQ, they decided that it makes sense to use a state pattern to avoid also allocating any closures. By their tests, it increased their specific use case scenario performance by almost 2 times. Another thing that we can use to improve performance, I failed to mention it last time because we delved straight into value tasks, but if you do not have a possibility to use value tasks, or you have some tasks that you just return, if you have a task and you return some value from result, let's say 100, and it's many times 100, you can always something like this. So you basically create a task in your class somewhere, a static task, and you cache it. You cache this value, and you return it always. Whenever you need to return the value of this task, you just return the instance of this task. So this way you will not create new tasks. You will always return the same instance of the task, and it will not be always allocated on the heap, and then it also needs to be collected by a garbage collector. So this is another way to improve performance by just caching your task results if you suspect that the result will be the same over time. One more thing that we forgot to cover is remember when we discussed synchronization primitives, I also told that there is more advanced stuff like memory barrier, volatile, etc. Well, I'll just quickly cover it here. So imagine you have a code like this, where in a while loop, you just on a separate background thread, you're just checking if the variable set is set, then you write in a value to console, and you stop. So it executes many times per millisecond until set is set. And as soon as it is set, you write in value to console. By default, set is false and value is 0. And you have a separate method that sets a value to 100 first, and then it sets a value of set to true. Well, there is a chance that after this code is run, this will print 0 to console. Because when you compile your code in release configuration, compiler does a lot of optimizations. And it can, for example, first set to true, and only then it can set value to 100. So it can switch these two statements like this without you even knowing about it. Because it doesn't analyze this code that's happening on some other background thread. It doesn't know that the specific order that you need to set these values is this one. You can prevent compiler doing such optimizations by using a method thread memory barrier. Thread memory barrier, it makes sure that the code that executes after memory barrier is always executed after the code that is executed before memory barrier. Alternatively, instead of doing that, you can mark a variable as volatile. So this will also tell compiler that it should not perform any optimizations around that variable. It's very rare where it's needed to use memory barrier or volatile. So in most of the cases, you will most likely use just regular login construction. And I personally never used memory barrier or volatile in any of my projects. So it's just something to know about in case you really have performance issues or you need to really tweak performance to the very, very top level and not use locking, but just make sure that the operations execute in the right order. And also last time we discussed lazy cancellation option of task continuation options. Well, I was a bit incorrect in telling what it exactly does. I rechecked it, and now I'll tell you exactly what it does on the example. So, see here we have task 1, where we just waiting for 5 seconds. Then we have task 2, which is continue with on task 1, and it just tries to cancel task 2, and also we supply here cancellation token. So whenever we cancel our cancellation token source, this second task should be cancelled. But later, task 3, we are running continuation on task 2 and writing task 3. So as soon as we call cancel after console read line, so I'll just press enter. During these 5 seconds, we'll cancel cancellation token source. As soon as we cancel it, task 2 should already be cancelled. Let's try this. 968, I'm pressing enter. And as you can see, task 3 is written to console instantly, even before task 1 is finished. And only after 5 seconds, task 1 have been finished. Why is that? It's because by default, cancellation happens instantly. And if this task is cancelled, even before this is completed, then this one will also execute because we did not specify here continue with only on successful operation. Continue with works either when operation is successful or it has failed or it has been cancelled. So this task is running. It doesn't matter what's the result of task 2. However, the issue here is that task 2 is cancelled instantly as soon as we cancel cancellation token source, even before task 1 has been completed. So to fix that, we can create task 2 like this. We can specify task continuation options lazy cancellation. This will make sure that task 2 also will be cancelled because we cancel this cancellation token source that we are passing a token from it here. But it will only be cancelled as soon as this task is complete. So it will be a lazy cancellation. It will not be cancelled as soon as we call cancel method. So if you rerun this example, you can see that we are waiting for 5 seconds, and only then it will be written that it will be written task 2 and task 3. So another option that we didn't cover on the task continuation options. We covered everything except execute synchronously. I'll just tell a couple words about this as well, so we all know about all the options possible. This basically means that the thread, the same thread that completed the first task. So if this task has been running on thread 7 and thread 7 has completed it, the same thread will be running this continuation. So continuation is picked up by the same thread that has completed previous task. This is what run continuation synchronously means. Execute synchronously. Yeah. All right, let's switch to further topics. First thing I wanted to also say, do not mistake task continuation options and task creation options. These enums named very, very similar, and like task continuation options, task creation options, and most of the methods like task factories, etc., they accept both task continuation options and task creation options. For example, continue with operation also accepts task creation options. So sometimes you can accidentally pass task continuation options as task creation options, and it might cause some issues because you will not expect that it would work this way. Tasks can be created by factory. So we can create a task like this, task factory start new, where we pass some delegate and we pass some creation options. These creation options can be passed here using this method. We cannot pass these options using task run method. So when you need some custom options, you need to use task factory start new. However, there is a separate way to create tasks. There is you can create an instance of task factory where you pass all the options that you need to have, like if it's attached to parent, continuation options, exclusive like scheduler, cancellation token as well. And then you can just use the method start new, passing a delegate. This way you can create many tasks with the same configuration options without specifying them many times. And this is an example of creating a task that is absolutely identical to the task that is created by task run. So this is an equivalent of task run. Here we can see how task run creates tasks. It has just two distinctions from not passing any options. First of all, it has task creation options deny child attach, as we discussed last time. So it will not allow any child tasks to attach themselves to the parent task. And second, it is using default scheduler. This is an important bit of information because usually tasks, when you create a not configured task, it uses current task scheduler. So if you have some parent task that uses a different task scheduler, custom task scheduler, and you create new tasks using just task factory without passing any options, you will inherit that task scheduler, and your child tasks will also use inherited task scheduler. This is the danger of using task factories instead of task run. You might accidentally use not default scheduler without even knowing about it. Task run always passes default task scheduler here, so even if parent task scheduler is different, your new tasks created by task run will run on the default scheduler, so just on thread pool without any specific behavior. A couple more things about exception handling. So as you remember, method wait or property result, they will throw aggregate exception with all the inner exceptions aggregated inside it. There is an easy way to flatten them all into one exception. You can use flatten exception method, which will throw aggregate exceptions that will not have many inner exceptions. It will have just one specific inner exception. I mean, it might have multiple exceptions, but they won't be aggregate inside. So it flattens the hierarchy of aggregate exceptions into just one aggregate exception, and all the other exceptions will be a target one. And also you can inspect a property on the task exception. If task is faulted, for example, this will not be null. And this exception has a method handle. This is an aggregate exception. This is why it has a method handle, where you can handle unhandled exceptions. So if your tasks threw an exception and you did not await it, you do not know even about it, you can always still handle those exceptions using this method. And it returns a Boolean flag whether it has been handled or not. Separately, task scheduler has a special event, unobserved task exception, which fires every time whenever task has through an unobserved and unhandled exceptions. I don't remember specifically when it fires. It might be firing on host stop or something like that, or maybe during some time interval. Yeah, I would need to check it, but the general idea that this handle method, it can handle your exceptions, and then this event will not fire for the ones that are handled. Yeah, since I have this method here, I assume that it is being called whenever garbage collector collects. So during finalizing of the tasks. Yeah, right, I recalled. Yeah, it's called during finalization of the tasks. Tasks have a finalizer that triggers that event. Returning tuple queue. As you remember, we have not tuple queue to parallel. As you remember, we have some method for each, even for async and for each async invoke. These methods also have additional initialization and processing delegates. Initialization delegate, it runs before each operation and it initializes some value and returns it. During the operation, you can get your index, the state to control state between operations, and a third parameter, you can get that initialized value that was initialized and returned in the first step. And after your operation has been run, you can return some value as well. And you can also run some delegate that will work on that value that you returned from your operation. So this is another way you can make more complex processing for your parallel loops. Also, there is a progress class in .NET. It provides you a way to, well, report progress. So like if you have a GUI application and you need to have a progress bar to show the progress, you can use this class. Why it is so good and what's the difference from just your own custom class that reports progress? This progress changed event, it will invoke your delegate on synchronization context. So it will post it to synchronization context. So this code will always execute on the GUI thread. So in your background threads, you can update this progress using method report, and it will be instantly reflected on the GUI because GUI will run this delegate and update some value on GUI based on that values that you sent in your report method. This is another example of the danger of using Task Factory. Task Factory does not work well with async delegates. It doesn't work with async delegates at all. It doesn't understand them because it doesn't accept async delegates here. Issue is that if we run this code, for example, we have a task created by the factory, we wait here for 10 seconds, and only then we are writing finished background task, right? If you run it, you'll see that application instantly finishes, and we wrote finished task in the console. This is because this factory, it actually creates this task and returns it. and it considers that it is what it has needed to do. So if you check the type of this task that we are awaiting, it's not just task, it's task of task. So the factory created for us task that has created this task. And since it's created instantly and synchronously, it's already finished by the time we call await. So in order to await for our inner operation, we will always need to call await task result, because result here is also a task. Task result will be a task that is actually our internal task. Now we'll wait for 10 seconds before writing this. This is one thing to remember when using task factories. One more thing I wanted to focus our attention on is never wrap async code around sync code and sync code around async code. It will lead to all kinds of issues. For example, here we have some method that returns task. And inside we're just calling task run and we're doing something synchronous inside. For example, blocking the thread for 1 second or calculating something. So from one point of view, it's good that we use task run, right? Because task run is usually like used for CPU bound operations, and this is CPU bound operation. So we delegated it to some background thread, and this background thread will be busy doing it. Issue here is that, I'm assuming that this is some library code. So issue here is that the consumer of this method, it doesn't know that your code actually creates a background thread that is being blocked. So imagine what if the consumer calls this method with await keyword. So it will await it, and it will call it on hot path in his web API, which is being called by 1,000 users. Well, he'll just start a thread pool and everything will hang. So whenever you return a task from a method, consumers will always expect the code to be non-blocking. So never do this. Instead, what you can do, you can just return do something sync. So you can have a void method and you can return do something sync. Let the consumer decide when to call task run. If he wants to wrap this operation in task run and run it on background thread, he will always be able to do something like this. Do not wrap it yourself and then just provide a blind method that actually blocks the thread. This is even worse because you returning a task, but this task will actually never be returned before the separation even completes. The separation will block current thread because you're calling synchronous method inside the method that should return task. Even if this method is async, you're still doing operations completely synchronously. This is another example of bad code. Vice versa situation, we have synchronous method and inside we just reused our asynchronous method, because why do we want to implement a separate method, right? We want to reuse existing logic. Well, when we block on async code, we introduce potential bugs. Namely, it can lead to deadlocks. So it is always preferable never to block on async code. What you can do instead is write a separate version of the method that is completely synchronous. You can reuse parts of code, or you can even reuse all the code with some private methods, but never block threads on async code and never wrap sync code inside async code. Before we jump into unit testing and debugging, I wanted to show you another issue. It's related to ASP.NET. So imagine we have ASP.NET application where we have a background service, which is just I-hosted service with some additional logic. And inside we have execute async method that returns task. We have that operation here, but inside we are sleeping for 1 hour. So I don't know, we need to do some synchronous operation for a very long time, and we are not returning the task until this operation is completed. Well, if I run it, the host will never start. It will hang. As you can see, no logs at all. Here I'm typing on my keyboard, nothing happening. It will hang for 1 hour because the ASP.NET expects that you return this task instantly. So you can either await task delay, or you can wrap your code into task run, what I just told you not to do. But I told you not to do it in library code when you return some task. This is our framework method, so we can easily do this here. Issue is that well, there is even a separate issue on GitHub on Microsoft side, which is still opened about this. So people do not expect this behavior. But from my point of view, it is understandable because framework expects from us a task. And instead of returning it a task, we are just blocking current method. So framework expected a task and it will expect it for 1 hour until we return it. So yeah, when you understand how all these concurrent parts are working together, you start to understand that this is expectable scenario. However, people think that it is a bug. So there is a bug on Microsoft side for that issue, which is highly debated currently, but Microsoft is still resolved not to solve it. They are saying that it is worked as expected. All right, let's switch to, before switching to debugging, I wanted to show you one case of unit testing because I don't have really much to talk about unit testing. I don't think there is a difference between testing non-concurrent code or concurrent code. There is no much difference. We can always split our code into testable chunks. I just wanted to cover here a new feature of the language that came to us in .NET 8, in the latest .NET, that allows us to test our classes in a very cool way. So let's imagine we have this class, message processor, and it has a method processing 5 seconds async, which waits for 5 seconds, and then it adds a message to the queue. This is a typical test for it. So we call this method, and instead of awaiting it, we are just assigning it to a task. Then we wait for almost 5 seconds. Then we check that message is still not added to the list. Then we wait for additional 500 milliseconds, and then we assert that the message is already in the list. However, this test takes 5 seconds, so it's not maintainable. Unit tests should be executed in mere milliseconds. It will slow down the whole test suite execution, which is why usually when you had some code like this, which waits for some specific time and you cannot abstract it away, we did not unit test such code. Or we introduce some custom interfaces or abstractions in order to not call task delay here directly, and then we use these abstractions to test our code. .NET 8 introduces a new concept. It introduces time provider, new class time provider. And in all the methods that delay for some time, like task delay here, they accept this time provider as a second argument. So this is rewritten better message processor that is unit testable. We can pass time provider into the constructor, and we can pass it in all our task delays. For example, here when we are waiting for 5 seconds, we are passing time provider. And this is a rewritten test. So we create a task from this method, and instead of waiting for almost 5 seconds, we are just calling time provider advance almost 5 seconds. We are checking the same, then we are calling time provider advance another 500 milliseconds. We are checking the same. So this test will execute in mere milliseconds because advance doesn't wait for anything. It just advances the time of that time provider. And for real code, this time provider will be just time provider.system. For our unit tests, it will be just fake time provider, which is also a class provided by .NET. So this is a way how we can test this code now. Very cool times. All right, let's switch to debugging. Just give me 1 minute. I'll be right back. All right, I'm back. So, debugging multi-threaded applications. This is a program written for debugging purposes. So here we, in while loop, just create a lot of tasks. Every half a second, we run another instance of do work, which creates some objects, then delays for 1 second, then it delays for another 5 seconds non-blockingly, but every dance operation will do it blockingly, so it will call thread sleep. And then we also exit from this task, but before we exit, we run on some another background thread, another task that will non-blockingly wait for 7 seconds. And then it will update the property of that object. So we'll generate a lot of tasks because this loop never stops. It will always set them every 500 milliseconds. Let's run this example. Yeah, I have breakpoints here. Let's remove them for now. As you can see, a lot of different threads starting to do our work. Some of them are the same threads because we are not blocking anything. And in some time also will start writing value changed, yeah, like this. So if we pause this application, we can see I usually prefer to have during multi-threaded debugging, I prefer to have a call stack window, a threads window, and parallel stacks window. It shows me the overall picture. We can see that we stopped on the main thread, so the first thread, the main thread. Threads window allow us to see exactly all of the threads that are being used by our application. There is a flag icon here, which is called flag just my code. So we can click on it. And as you can see, only 2 threads have been flagged, the first one and 11th. So all the other threads are not doing anything, they're not doing anything in our code. We can switch to thread 11 by either right-clicking on it and selecting switch to thread, or we can just double-click on it. And we'll see that this 11th thread is actually our 10th operation that is blocking for 5 seconds. So it has been blocked for 5 seconds, our operation. All the other operations that are using awaits, they will be very hard to actually catch here on the threads window. We will need to use either breakpoints or increase the decrease this value, because well, since we are not blocking threads, we have some tasks waiting here, but tasks are not threads. Threads are not being used at the moment. However, we can still see all the tasks that that we have in our application. We have tasks, separate tasks window, where, as you can see, we have a lot of tasks. It also shows us location. So let me just make this window bigger. It also shows us location where this task is originated. So for example, this task is awaiting here. We can also double click on that on them and switch to them. I mean, we cannot switch to them because no threads are currently running them, but we can kind of switch to them. So the code will show us where this task is being executed. So this task is awaiting on this line. This task is awaiting on this line. Also on our parallel stacks window, we can switch to a tasks view. So tasks view will show us that, for example, there are 14 tasks. This number shows us the number of tasks that have called this anonymous method, this one. And then this method called update async method. And we are currently on this line if I click on this update async method. Also, if you hover and wait on this update async method, you can see the list of all the tasks that are currently awaiting here. So we can see there are quite a bit of tasks that are currently waiting here. 11 tasks are currently awaiting on this line. So we can also see all 11 tasks if we hover here. Yeah. And one task is just awaiting on task delay. So this is our main thread that is awaiting. One task is blocked here. As you can see, there is an icon with this circle that is crossed. It means that the thread is being blocked. So as you can see, thread sleep, we have only one thread that is blocked, no other threads are blocked. And all in all, 1 plus 11 plus 14, we have 26 async logical stacks that are all calling something together. As you can see, we cannot see what exactly because it shows us external code. However, we can also see all the external code that is being executed in our application by clicking this button, show external code. So if we click it, we can see that, for example, our task that is blocked, it is executing thread sleep. Our one async logical stack that called task run, it is currently just waiting for something in .NET. Yeah, if you double click, you can even go to the .NET source code, like future CS class is called. And you can even see what is going on there. You can even debug it. And all our these async logical stacks, they all call in task delay, as you can see. Yeah, we can also go inside task delay and see what is happening there. If we are interested in some specific method, for example, we are interested in this update async method, we double click on it, we can switch into function view. This button opens up a method view, toggle method view. Method view will show a flow of stack frames just for this specific method. All the other stuff will be removed. So if I click on it, you can see that task run called our method anonymous method, then anonymous method called update async, and then update async called task delay. We can always switch to another frame of this stack trace. For example, if I double click on anonymous method, now function view shows us the whole picture regarding anonymous method. What has called anonymous method and what this anonymous method is calling. Now, this is a task view. There is also a threads view. If we switch back to threads, we'll see that, and I remove external code because external code runs on different threads. We'll see that there are 5 threads currently that are calling this thread sleep method. Let me just show external code. Yeah, this is a bit incorrect picture. I don't know why parallel stacks shows it this way. Maybe it's even a bug on Microsoft side, but it's a bit more precise to look at the threads picture with show external code enabled, because here you can see that we actually have 5 worker threads in thread pool, but 4 of them are completely doing nothing. They're waiting for signal, they are free, and only one of them executed all these methods, which led to our do work async method, which is actually now sleeping on the thread. And you can also use method view in thread context. So you can see that this thread is called all these methods, and the work async called thread sleep. Now imagine that we need to watch this variable work. So we create a work and we are watching for its value. So this is its value, ID, index, nested, prop1, prop2. If I put the breakpoints here and I press F5, you can see that first of all, watch window, it highlights all the changed values with red color, which is very handy. We can see instantly what has changed. So if I click F5 again, you'll see that it always changes. So we jump through different threads. However, we cannot, if, for example, other threads are executing in the same method at the same time when we post our application, we do not see these values. But we can easily see them. There is a separate window, parallel watch, which is a watch exactly for debugging concurrent applications. Instead of adding values in the column here, we are adding here in the rows. We are adding it in the column. So here we can write work, or maybe let's write work.id to check its ID. And as you can see, at the current time, at the current moment of time, in this method, we have 2 threads, 6004 and 14588. They are both somewhere in this method, and in one thread, this value is this one, and another this one. We can also switch to this thread by just double-clicking it. So you can see that this thread is actually standing here. This thread is actually standing here. Also, whenever we switch between threads, if you can see here on the left, there is a very little blue dot, a blue exclamation sign. This exclamation sign means that we have switched into another thread. Let me just show you an example. So if I'm standing on this thread and I click, let me just maybe put a breakpoint here. If I'm standing on this thread and I click F10, see, it didn't go to the next line. It jumped to another thread because another thread needed to execute that instruction. And this blue exclamation sign has appeared. If I click F5, it will appear again because we again switched threads. But if we do not switch threads, if I click F10 and it will actually go to the next line, well, of course it didn't, but if it would, we would not get that blue exclamation sign. So this is an indication that the thread has changed. Another useful feature is we can actually see all the threads that are staying on different places of this method by right-clicking on the threads window and selecting this option, show threads in source. This option is false by default because it incurs some performance hit. So debugging will be a bit more slow. But if you enable it, you can see that on this line and on this line, there is blue lines like this. One is like this and another one like this here. You can barely see them on, like if I disable breakpoint, yeah, you can see these 2 lines. It means that some different thread is staying on this line. And if you hover over it, you can even see it, 6004. So we are currently on this thread, 3472. It is denoted by this yellow arrow. Yellow arrow shows us which thread we are currently on, this one. It also should be marked. Let me remark all the threads. You see, currently our code is being executed by 4 threads. And this 6004, it's also somewhere in our method, but even without switching to it, we can instantly see where it is. We can just see that there is some thread here, and if we hover over it, we can see that it's 6004. We can also write from here. We can freeze it, we can switch to it, and we can unflag it or flag it, because we flagged it, so we can unflag it. By the way, this window also allows you to filter all the other threads. So since we are not interested in .NET threads and all the free threads of thread pool, we can click on that button. It will show on us only flagged threads. It will also update parallel stacks window. So on parallel stacks window, we will only see our flagged threads. So only the threads that are currently executing our work. One cool feature of the watch, by the way, parallel watch doesn't have this feature, so it's really not related to concurrency. But since we are talking about watches, I'll just show you. We can search for values here. For example, if I click 2, 4, 3, it instantly finds me this property. And it can search really as deep as 10 different nesting levels. And it will even search objects in lists, in dictionaries, etc. So if you just add some dictionary to the watch here and you input something here into the search, you will instantly find the object that you're looking for. And since we're talking about parallel watch, yeah, it's also not about concurrency, but parallel watch can be used for another very cool feature. Imagine we have a recursive method like this. So it will just take our Ivan string and it will call itself with doubled the string. So it's a recursive method that will never stop executing and will always double the value. If we run it, we can add here our value. So different threads will not execute it, obviously, because it's a synchronous method. But if we click F5, you can see that another value appears here, which shows us a new value, Ivan. And here it also shows you recursion depth. So it shows you recursion depth 0, 1, and if you click F5, it will be 2, and it will become 4 times Ivan. If you click F5, it will become 8 times Ivan. And this way, we can really very easily look at what our recursive method does. So it's a very handy feature to debug recursive methods, this parallel watch window. One more thing I want to say is that Visual Studio, actually the latest Visual Studio, is very cool. It allows us to debug external code, Microsoft code, or in libraries code, like ReSharper did in the past. And it doesn't even require PZP files. So it takes the source, it decompiles it, it compiles it back into C#. In the process, if it is optimized, it also de-optimizes it if you stepped into it. So the parts that where you stepped into, they will be de-optimized. And then you'll be able to debug internal code of any method or any object. In order to do that, it's very simple. So, for example, we have a task here. Let's debug method task run. So we start an application. And we just step into it, but it doesn't work, right? Well, it's because currently we have just my code, this option, enabled. We can disable just my code, which will do one thing. It will make Visual Studio think that all the codes that we are currently running, all the libraries, all the DLLs, everything, it is actually our code. So in regards to concurrent applications debugging, it's not very good, because now if I mark here just my code, flag all the threads. As you can see, all the threads are flagged, even free threads of thread pool, etc. It's because Visual Studio thinks that all the threads are running our code currently. But what it allows me to do, it allows me to step into task run methods. As you can see, I stepped into task run method of .NET, and then it called some internal start new method, into which I can also step into, and I can go through different, I can inspect all the variables, etc. So yeah, let me just disable just my code. Yeah, also on the parallel stacks window, you will not even have that button, external code, because it will always show all the code if you have just my code disabled. Now imagine we have so this application where we are executing this method for every time I press enter in console. Yeah, right. First need to select the example. So I'm pressing enter. Let me just press enter a couple more times and see. Imagine this method is being called by some different threads. So I came here. I want to debug this method execution. So I click F10. Okay, we went to the second line. I click F10 again. But what happened? I went backwards. So it happened because another thread has come to this method, and we have a breakpoint here. As you can see, this blue dot is showing us that there is some different method here. And as you can see, we have another method on this line. So there are two blue lines here showing that there are two methods currently. Also, parallel watch shows us these two different threads at the moment. Imagine I want to continue debugging the first method. What I can do is I can freeze current thread. So this is the current thread that intervened in my debugging experience. I can right click it and select freeze in order for it to just freeze and wait. And I click F5, another thread came here. Okay, let's freeze it as well. Freeze. Let me just freeze this as well. Okay, I continued debugging my first original method. I click F10, another method came here. Let's freeze it as well. Click F5, another method came. Yeah, I pressed enter quite a bunch of times. Okay, I'm continuing. Now all the threads are freezed. I'm continuing debugging. I'm continuing debugging. Okay, I debugged my one method. I click continue. Now I can just pause application again, and I can see that 5 threads are currently paused. If I flag them, they will also show as my code. I can switch into any of them. I can also unfreeze any of them and keep debugging specific method after I unfreezed it. So this way you can synchronize your debugging between different threads. Yeah, if you do not want to use this window, also you can always switch threads here. This is also a window where you can switch between different threads. And here you can also switch between different stack frames instead of using parallel stacks window or call stack window. Call stack window also, yeah, it shows us our call stack where we can also double click and switch into specific methods that executed our code. If I unclick this button, show external code, then you'll see that only one line is shown here because we did not call any methods from our own methods, only external code called our method. This button, by the way, it works between both windows. So as you can see in parallel stacks, I click it here, or I click it here, it will show or hide external code in both windows. So breakpoints. How can we use breakpoints in order to debug concurrent applications? First of all, it's not related to concurrency really. I just wanted to tell about it. It's a new feature of new Visual Studio. It's a handy feature. I find it useful. In breakpoint window, we can group breakpoints now. So we can create group. We can put multiple breakpoints in that group. We can disable or enable breakpoints in one group. And we can also create a default group where all new breakpoints will be added. So there is no need to, like, we can organize them. When we create breakpoints for our application, we can have actions or conditions here. So for conditions, we can write here some condition, for example, only break on some specific thread, or only when some value is some value. It also can help with concurrent debugging. But also there are actions here where we can write to put something into our output window. It's almost the same as login. So it is called a trace point and not a breakpoint when you have this setup. And when you have many threads running at the same time and you cannot afford to pause your applications, it's a really viable way to find out what's wrong. I prefer using login, honestly, but you can also do it with trace points. Also, you have an option to disable breakpoint once hit. So if you want to debug just one thread while allowing all other threads to be run, you can always check disable breakpoint once hit, and as soon as your first thread will hit it, all the other threads will not hit it anymore because it will be disabled for them. And also breakpoints can be dependent on each other, so you can allow this breakpoint to work only after another breakpoint has been hit. And this way you can make complex chains of breakpoints. Now, when you created some complex breakpoints with chains, with conditions, with trace points, if you need it in some other place, you do not need to create it all again. You can just drag and drop it. Yeah, breakpoints can be dragged and dropped. I also didn't know about it until recently, but it's a very handy feature. For example, this breakpoint that is currently dependent on another breakpoint, I can just drag it into another place and not set up it all over again. One more thing is, returning to this example that was creating an object. Imagine if we need to break whenever this property changes. So here we are changing this property after 7 seconds. So we want to break when this property changed. However, we want to break only on some specific object instance. So for example, I place a breakpoint here, I wait until it is hit, and here we created some instance. And I want to continue and keep applications going, but I want to break next time when this property changes, but only on this specific object. Well, in watch window, we can also create an object ID from some object. We can click on the object, and there is an option make object ID. Make object ID will show you an object ID. It's $1. And we can place another watch here, $1. And this $1 will be specific object, this specific instance. So if I click F5, you can see that the first object changed because it is monitoring just work variable. But this object didn't change because we are specifically monitoring previous object that we just created an object ID for it. And now if I want to break whenever this property changes, I can just right click on it and I can select break when value changes. I can also insert different breakpoints or trace points right here, but for this example, I want to break when value changes. So I click on it. As you can see, there is an icon of breakpoint shown right here. And now if I just click F5 and I just disable this breakpoint and click F5, then in about 15 seconds after this has run and this has run, this property will be updated and my breakpoint will be hit. Yeah, as you can see, it is hit on the set. So it is set. I can just click F10 to continue execution. And as you can see, it has some new value. Also, there are exception settings. I will not delve into it because we are already today's meeting is planned for 90 minutes, but anyway, there is a separate exception window where we can set up exceptions. So we can set up some exceptions to be thrown from our code, some that will not be thrown. There are also different conditions for them to be thrown. For example, if it happens in your project with this namespace, then throw it, or on the contrary, not throw it. So you can all configure it in exception settings. It's a separate window. Yeah, and one more thing I wanted to say about Visual Studio as a whole. You can move all the windows, right? Here, or you can move it maybe here. And for ultra-wide monitors, you might want to place them on the side, or for vertical monitors, you might want to do this. My advice is do not be afraid to experiment with this, because even if you completely screw up your layout and you want to revert back to the way it was, you can use a feature that I'll describe right now. It is a feature that has been very, very long in Visual Studio already for a very long time, but I just found out about it recently, and it increased my productivity a bit because I am able to use different window layouts for different flows. It is window layouts. So you can save a window layout and then you can reapply it after you change some windows and you do not like it, or if you just want to switch into a different window layout. For example, let's show breakpoints and put them here. And imagine that I don't like it. I have a separate window layout created for the sake of this presentation so that Visual Studio looks decently on Full HD resolution, because I'm running Full HD resolution just for presentation so that it's visible for everyone. So this is how it looks. It's just a window with Solution Explorer. Whenever I want to code something, I have a separate window layout code editing, where it's, well, yeah, it's a bit different and it's different in debugging scenarios, but it's very similar. For unit testing, I have this layout. I usually also run two windows here with the code. It obviously doesn't look like that because I have an ultra-wide monitor, but yeah, you get the idea. So you can always create these layouts and you can experiment with them without fearing that you will not be able to roll back. This way you can create an optimal layout that works for you. One more cool feature of the language is in .NET 9 that will come out from November. They changed how asynchronous exceptions are happening. So previously, if you did not catch your exception that is thrown from the code that you are running from some framework. So for example, from Vue framework or from some ASP.NET that is being called by different middleware. And if that middleware also didn't catch it, then stack traces were very confusing and it wouldn't even throw from your code. However, starting from .NET 9, exceptions will be thrown exactly from the place of code where they are thrown. So Visual Studio will show you the place of your code where this exception is thrown, even if your code is just being called by some other framework that is calling it and then not handling it. So that's a very cool change. I'm waiting for it eagerly. Unfortunately, it will only work for the project that was created with .NET 9. So we will also need to update our projects. And another cool feature, I guess, of Visual Studio that is not related to concurrency, but I just wanted to also advertise it. I have an application on a remote local on a remote machine on DigitalOcean server, to be honest, that is being run under Linux container built completely in release configuration. And I am able to attach to it using Visual Studio attach to process, attached separate server through SSH on which there is a Docker running. So I'm attaching to separate server through SSH into the Docker container in which my application is running that is built in a release configuration, and I am able to debug it with all the breakpoints being hit, etc. I did not even expect it to work because I didn't build this application specifically for debugging. It just works. So this is how Visual Studio is very powerful lately. If you need to debug some external application and you have access on network level to it, you might just want to try to attach into that process and try and debug it. The only caveat is your source code should obviously be absolutely the same as the code on a remote machine, and you should enable just my code option because it will not work without it. But if you disable just my code, it should work. I guess we covered most of it. I might have some additional things to discuss if we still have time, but let's first, let's have a short pause for now, and I'll just ask if anyone has any questions regarding everything, all the 7 parts that we covered, because today is the last part, so now will be the time to discuss anything you want to discuss, concurrency related, that you want your questions answered, or just to discuss something.
Hey, Ivan.
Yeah.
I have some. It's not exactly a question, but yeah, I just hear the silence, and I want to add something regarding breakpoints. That in breakpoints window you can even specify. Yeah, could you just open it? Yep. There you can specify the exact method name and which should be triggered.
Yeah, right.
Yeah, if you want to debug, for example, some external library and you don't have an access, for example, to files during debug process, you can type function name, and it's really powerful feature. And
Yeah,
I've used it. It
that's
helped me.
a great note. Thank you. Yeah, we can specify here a method name. I also try to use it sometime. It will search all the code for these method names, and it will add breakpoints for all the methods that match its name. So yeah, when we don't have access to some code, we can just enter it here, and it will create breakpoints for us. That's a handy feature. It's a shortcut for this Control KB. I'm not sure how to do it through this window, to be honest. I never did it through the window. Yeah, function breakpoint. So it's new function breakpoint. Yeah, all right, Control KB. Yeah, Visual Studio has a lot of cool features, but I'm sure I know only like 5% of them. So any other questions or suggestions? If you're talking about breakpoints, and since we still have 10 minutes and no questions, I'll just then show you some more cool stuff, I guess. So there is also a breakpoint. There is also a disassembly window. Windows. Where is it? Yeah, we need to start debugging in order for these items to appear here. So there is also disassembly window that actually shows you the disassembled code. So I'm personally, I am not very familiar with disassembly code, so this window is completely useless to me. I not reached yet this level of low-level understanding. But if you know your stuff around it, you can even place breakpoints here, and they will be hit, or you can go line by line in this assembly window. Like you see, here is some item here, and it performs instructions one by one. So yeah, for just one method in .NET, you might need to pass 20 of methods here. And CorpFX team in Microsoft that is currently developing the core.NET runtime and the JIT compiler, they are working with this window. So I guess they created this window just for themselves, most of all, because their whole work is wrapped around this window. They are spending in it 24 hours per day, and this is how they are making all these cool changes in the language that are bringing us so much performance benefits. So they are investigating this window, they are seeing what instructions compile into what code compiles into what instructions, and they optimize it and improve. All right, let's see that exception settings window. View. Actually, yeah, there is another very cool feature of Visual Studio, which, as you can see by my futile attempts to find some stuff in these menus, it's called feature search. So you can just click Ctrl-Shift-P, and you can search for any features that you want. For example, exception settings. Yeah, this is the window that I was trying to find. So here in exception settings, we can set different exceptions. For example, if you want to your code to not throw invalid operation exception, you can search for it. And here you can either uncheck it, then it will not be thrown at all. So whenever your code will throw invalid operation exception, it will not be thrown. I mean, it will be thrown. It will not be shown by Visual Studio. It will not break on it. And if this exception isn't handled, your host will just crash. If it's not, then it will maybe be logged if you're logging it, or maybe it will not even be logged if you're not logging it. It will be just silently swallowed, and you will not know whether invalid operation exception occurred in any place in your code. Alternatively, you can edit conditions for it. So you can only break on this exception where module name is not equals, for example, to concurrency console application. This condition ensures that invalid operation exception breaks whenever or equal, better equal. Yeah, it ensures that invalid operation exceptions are not equal. Does not break. It ensures that it breaks when the module is not our code. So it will break only if external code throws this exception. If we select equals here, then it will only break if our code throws it. If external code throws it, it will not break. So in this way, we can configure the exceptions here. If you just select everything here, do not do that, but if you check everything here, then Visual Studio will constantly pause all the time because there are many exceptions happening in the runtime under the hood sometimes, and it might just break every time something happens in external code then. And one more tool that I wanted to discuss, whenever we are debugging concurrent applications, usually we are synchronizing between different threads, and these simple scenarios that I showed here, they are not enough. Maybe we have a bug that is happening only when application is running on some environment or even locally, but you cannot reproduce it when you pause the application. So it happens only during runtime. So for concurrent debugging, logging is really unparalleled. And recently I found out a very good tool. So it's a bit of, I guess, an advertisement, but this tool is completely free, open source, and you can use it without any legal issues, etc. So it's just a personal experience with this tool, so I will share it with you. It is called CQ. So it's a database, let's say, for serial log. This is a very easy way how you can run it on your machine. So there is a one-liner that runs it inside Docker on your machine. It just stores all the data in the folder D MySecure storage. So on folder on disk drive D, you will have this folder, and all the data will be stored there. And this is a very easy way to configure it in our .NET host. So you can just install CQ package, and then you can just specify here your static IP address, or if you're running it locally, 127.0.0.1, so your local IP address, and API key, which you can get from CQ dashboard whenever you start this CQ. And what it does, it gathers all your logs that you're writing, for example, using structured login. And you can create different dashboards like this one, based on that data. So these are dashboards created just for my own pet projects where I'm gathering all the logs. And this is example of the logs. So you can inspect every item. You can see different properties that you're logging. So it's very handy for debugging concurrent issues. Logging in itself, not secure. So if you are having logs in, I don't know, up inside, and you have some concurrent bug, really, for concurrent debugging, I'd say logging is in parallel. You can achieve similar effect with trace points. So if you want to really catch that bug in local environment, you can use trace points in order to set up some breakpoints that do not actually break your applications, but they will be writing stuff into this output window debug. And yep, I guess then we can wrap up this call. I will just ask one more time if anyone has any questions.
Not question, just thank you for such graceful journey.
Yeah, my pleasure. So guys, it was a fun experience. Thank you all for joining all these 2 weeks. Have a good weekend and see you in future sometime if I decide to talk about something else.
Thank you.
Thank you.
Thank you.